Fire is not a thing you can hold. It has no weight, no fixed shape, no surface you could touch and find solid. It is a process, a rapid release of energy as matter transforms, and yet it has lit every human night for 1,000,000 years. Welcome to the Sleepy Lab. Tonight, we drift through fire, what it actually is, where it came from, and why this ancient, weightless process may be woven into the very structure of who we are. If this kind of quiet wondering helps you sleep, consider subscribing. One sleepy soul at a time. Now, let's begin. Somewhere in the universe, right now, there are stars collapsing, galaxies turning slowly in the dark, clouds of gas drifting across distances too large to hold in the mind. And yet, as far as we can tell, in all of that vastness, there is no fire. Not the kind burning in a candle, not the kind that once crackled in a cave. Open flame, the kind you can watch and feel, appears to exist only here, on this one small planet, wrapped in just the right kind of air. That is worth sitting with for a moment. Fire is not matter. It has no mass. If you tried to weigh a flame on a scale, you would find nothing there, because a flame is not a thing. It is a reaction, a rapid exothermic oxidation, as chemists would say, which simply means certain molecules are breaking apart and reforming, and in doing so, they release energy as light and heat. The glow you see is not a substance. It is a process, happening continuously, sustaining itself for as long as the conditions allow. And those conditions are precise. Fire needs three things, all at once. Fuel, something that can oxidize. Heat, enough to start and sustain the reaction. And oxygen, free oxygen, present in the surrounding air. Remove any one of those three, and the fire simply stops. Oxygen is the most delicate part of that balance. For fire to sustain itself, oxygen must make up at least roughly 16% of the surrounding atmosphere. Below that threshold, flames cannot persist. Earth's atmosphere sits at about 21% oxygen. That is closer than it might seem, to the upper edge of what is safe. If oxygen levels rose to roughly 35%, the world's forests would burn almost without pause. A single lightning strike, a single spark, and the land would ignite and keep igniting. We live, it turns out, in a narrow band of possibility. Enough oxygen for fire to exist. Not so much that everything burns. It is a balance that is held, more or less, for hundreds of millions of years. The earliest confirmed evidence of controlled fire by human ancestors dates to about 1,000,000 years ago. It was found in a cave, Wonderwork Cave, in what is now South Africa, where researchers discovered burned bone and plant ash, deep inside the rock, far from any entrance where a natural fire might have reached. Someone carried fire in there, or made it there, and sat beside it. Some researchers believe the relationship between hominins and fire may go back even further, perhaps as far as 1.5 million years. The evidence for that earlier date is less certain, more debated. But the possibility is there, quiet and patient, waiting in the sediment. The species most closely associated with the earliest deliberate use of fire is Homo erectus, an ancestor who walked upright, ranged widely across the ancient world, and, at some point, learned to keep a flame alive. Homo erectus was not us. Not yet. Homo sapiens, our species, would not appear for hundreds of thousands of years after fire was already in use. We were born into a world where fire was already known, already tended, already part of what it meant to be human. Or rather, fire helped make us human. The ability to control fire is considered, by many researchers, one of the most consequential developments in the entire history of life on Earth. That is a large claim, and it is worth letting it settle slowly. In all the billions of years that life has existed on this planet, through every adaptation, every extinction, every branching of the tree, the moment a hominin first held a flame and chose to keep it may stand apart. Not because fire is dramatic, but because of what it quietly changed. It changed what we could eat. It changed when we could be awake. It changed how we gathered, how we spoke, what we remembered, who we became. But those changes, the cooking, the brain, the long evenings by the light, those belong to the next part of the journey. For now, just hold this. Somewhere in a cave in South Africa, 1,000,000 years ago, a fire was burning. The bones of animals lay in the ash. The walls of the cave held the warmth. And something that was almost us, something that would, in time, become us, sat close to the light. The same light that is, in some sense, still burning. Fire is not matter. It cannot be weighed or held, and yet it has been with us longer than language, longer than memory, longer than anything we could call civilization. It is a process, a transformation, energy moving from one form into another, releasing itself as warmth and light. And somewhere in the oldest, quietest part of you, the part that existed long before you had words for any of this, that warmth is still familiar, still safe, still home. So let us follow that warmth a little further. Fire did not only keep the cold away, it changed what food could become. When heat meets raw meat, or a root pulled from the ground, something quiet and profound begins to happen. The long protein chains start to unfold. The tough fibers that would have taken hours of chewing to break down begin to soften. The cell walls that locked away their energy start to open. Cooking is, in a sense, a kind of pre-digestion. The fire does work that the body would otherwise have to do itself. And the result is remarkable. The same piece of food, cooked rather than raw, delivers significantly more usable energy. Not because new calories have been added, but because more of what was already there becomes available. The body can absorb it. It can use it. For millions of years before fire, our ancestors spent enormous amounts of time and energy simply chewing and digesting. The gut of a great ape is long and complex, built to extract nutrition from raw, fibrous plant matter through slow, laborious processing. It is a system designed for a world without fire. But something shifted. A primatologist named Richard Wrangham spent years thinking carefully about this question, about what cooking actually did to the human body over deep time. His proposal is quiet, but far-reaching. He suggested that cooking did not merely make life more comfortable, it may have made us who we are. The human gut, compared to that of a chimpanzee or a gorilla, is proportionally smaller, shorter, less elaborate, as though it no longer needed to do quite as much work. And if the gut required less energy to maintain, that energy could go somewhere else. It went, Wrangham proposed, to the brain. The human brain is an extraordinary organ in many ways, but one of the most striking is simply how expensive it is. It accounts for roughly 20% of the body's total caloric intake. A fifth of everything you eat goes to keeping that 3-pound structure running. Thinking, remembering, dreaming. All of it costs energy, continuously, even now, as you lie still in the dark. For a brain like ours to exist, the body needed a reliable surplus, a way of getting more energy from food than our ancestors had ever been able to extract before. Fire may have been that way. Not directly. Fire did not feed the brain, but it unlocked calories that had always been there, waiting in roots and tubers and meat, inaccessible to a body that could only eat things raw. It created a surplus, and over hundreds of thousands of years, that surplus may have quietly funded the expansion of the most complex structure in the known universe. There is something almost tender about that idea, that the brain you are using right now, the one that holds your memories, your language, your sense of who you are, may owe some part of its existence to a fire someone built a very long time ago. And there is more. Cooking softened food, not just chemically, but physically. Food that has been heated becomes easier to bite, easier to chew, easier to swallow. And over generations, a body that no longer needed to grind through tough, raw fibers all day long began to change its shape. The large jaw muscles that other apes rely on, muscles so powerful they anchor to the top of the skull, began, slowly, to reduce. And as those muscles became smaller, the skull was no longer constrained by them. It had room to grow outward, to expand, to accommodate what was growing inside. The human face is flatter than that of any other ape. The jaw is shorter, the brow less pronounced, the whole structure more delicate. It is a face shaped, in part, by the softening of food, by the long, slow consequence of heat applied to a meal. We carry the history of fire in the shape of our own faces. And then there is the night. Before fire, darkness was a boundary. When the sun went down, the day ended. There was little to do but sleep or stay very still and wait for morning. The world after dark belonged to other creatures. Fire moved that boundary. A fire burning at the entrance to a shelter or in the center of a camp pushed the usable hours of the day outward into the evening. There was light to see by, warmth to sit near, safety enough to stay awake and be together. And in that new time, that quiet space between the end of work and the beginning of sleep, something began to happen that may have been just as important as the cooking. People talked. An anthropologist named Polly Weissner spent time with hunter-gatherer communities and paid careful attention to what people actually said to each other. And when, during the day, the conversations were practical: where to find food, how to make a tool, what needed to be done, the talk of a working world. But at night, by the fire, something shifted. The conversations changed. They became longer, slower, more wandering. They filled with stories. Stories about people who were not present, about events that had already happened or might someday happen, about the world beyond what could be seen or touched. Storytelling, memory, the imagining of other lives and other times. These are among the most distinctly human things we do, and they may have found their first real home in the hours that fire created. The firelight flickered, the voices rose and fell, and something that we might recognize as culture began, quietly, to take shape. Fire also carried people into places they had never been. Our earliest ancestors were tropical creatures. They evolved in warmth, in the long light of equatorial Africa. Cold was not something their bodies were built for, and for a very long time, the colder regions of the world were simply beyond reach. Fire changed that calculation. With a reliable source of warmth, with the ability to heat a shelter and cook food that would sustain a body through a cold night, early humans could survive in climates that would otherwise have been fatal. They moved north, into Europe, where winters were long and dark, into northern Asia, where the cold was deeper still. The world opened. Not all at once, not quickly, by any measure we would recognize, but over thousands of generations. Fire extended the range of the human animal until it covered nearly every corner of the earth, from the tropics to the edge of the ice. All of that movement, all of those migrations, those new landscapes, those new skies seen for the first time by human eyes, carried in them the warmth of a fire someone had learned to keep burning. It is a long chain, and it reaches all the way to here. To you, lying still, breathing slowly, in a world made possible by a process that began before memory, before language, before anything we could call a beginning. The fire is still with you, in the shape of your face, in the size of your brain, in the stories you carry, in the warmth you still seek at the end of a long day. It has always been with you. And fire was not only warmth, it was a tool. Long before metal, long before the wheel, early humans learned that a wooden spear tip held in flame for a time would emerge harder, denser, more capable of holding an edge. The heat drove out moisture and changed the structure of the wood itself. A simple stick became something more, something that could be trusted. And with that harder tip, the hunt changed. Fire was used not only to sharpen tools, but to direct the animals themselves. A line of flame, or the threat of it, could move a herd, could press them toward a cliff edge, or into a narrow place where they could not scatter. The fire did not need to touch anything to do its work. The sight of it, the smell of it, was enough. Animals that had evolved alongside fire for millions of years knew what it meant, and they moved. So the hunter used that ancient fear, quietly, deliberately, as a kind of language spoken to the landscape itself. And the landscape listened. Fire cleared ground that would otherwise have taken generations to open by hand. Dense undergrowth, old growth, tangled brush, all of it could be reduced in an afternoon. What grew back afterward was often softer, greener, more inviting to the animals that humans needed. The land was being shaped, not yet farmed, not yet owned in any way we would recognize, but tended, managed, remembered from season to season. This was not destruction. It was conversation. And some of what fire touched, it preserved in ways no one intended. There were baskets in those early camps. Baskets lined with clay to make them hold water or food. And sometimes, in the ordinary chaos of a fire, one of those baskets would fall or be left too close. And the clay, exposed to heat it had never known, would harden, would become something new, something that held its shape long after the basket itself had burned away. The first pottery may have been an accident, a moment of loss that became a discovery. The clay remembered the fire and kept its form. And the charcoal left behind in those ancient hearths, the blackened remnants of wood that did not fully burn, that too persisted. Charcoal is among the most durable materials that archaeology has. It does not rot the way bone can. It does not dissolve the way softer organics do. It simply remains, patient and dark, waiting in the earth for someone to find it and ask what burned here. And when some of that charcoal is millions of years old, it is a record written in carbon, the most honest kind of record there is. And all of this, the hardened spear, the cleared hillside, the shaped clay, the ancient ash, all of it came from the same quiet process, the same reaction that is happening right now. If you picture a single candle flame, look at it in your mind, that small, still shape. It seems simple, but it is not. The color of a flame is a map. Every shade tells you something different about what is happening at that exact point in the fire. At the very base of a candle flame, where the wax vapor first meets the air, the combustion is most complete. The temperature there is highest, and the light it gives off is blue, a deep, quiet blue that most people never notice because the brighter orange above it draws the eye. That blue zone can reach temperatures near 1400 degrees Celsius, hotter than most things you will ever encounter in ordinary life. And yet, it is the quietest part of the flame to look at, the least dramatic, the most easily overlooked. Above it, the flame opens into orange and yellow, and those colors come from something specific. They come from tiny particles of carbon, soot, essentially, that have not yet fully burned. They are glowing because they are hot. The way a piece of metal glows red when you heat it, not because of the chemical reaction itself, but because of the heat that reaction produces. The orange you see in a candle flame is the light of glowing solid particles, incompletely burned, still in the process of becoming something else. And the cooler outer edge of the flame, where the temperature drops and oxygen is thinner, glows a deeper orange still, the last light before the fire gives way to the dark. Every color, every gradient is information, chemistry made visible, temperature written in light. It is one of the more quietly remarkable things in an ordinary room. And then there's what happens when you take that flame somewhere gravity does not reach. Astronauts on the International Space Station have lit candles in the course of experiments, and what they found was that the flame did not look like a flame at all, by any familiar measure. On Earth, the hot gases produced by combustion rise. They rise because they are lighter than the cooler air around them. And as they rise, they pull fresh oxygen up from below. That upward flow is what gives a flame its shape, the elongated teardrop, narrow at the base, widening and tapering toward the tip. That shape is gravity's signature on fire. Remove gravity, and the signature disappears. In microgravity, there is no convection, no rising column of hot gas. The combustion products simply spread outward in every direction equally, and the flame becomes a sphere. Small, dim, and almost entirely blue, barely visible, burning cooler than any candle flame on Earth. It is a strange and quiet thing to consider, that the shape of a flame, the shape humans have watched for 1,000,000 years, the shape that has meant warmth and safety and the end of darkness, that shape is not intrinsic to fire at all. It is a gift from gravity. Without the pull of the Earth, fire loses its familiar form. It becomes something almost unrecognizable, a pale blue sphere, hovering, burning without drama, without the flicker and reach that the human eye has always known. And perhaps that is part of why fire feels so particular to this world. So particular to here, the flame you know, the one that dances, that reaches upward, that throws orange light across a dark room. That flame is shaped by everything that makes this planet what it is. The oxygen in the air, the gravity beneath your feet, the fuel that grew from soil and rain and sunlight over years. It is not a universal thing. It is an earth thing. A thing that belongs to this place, and to the long story of the creatures who learn to tend it. And you are one of those creatures. Lying still now, breathing slowly, carrying in your body the long memory of fire, the hardened spear, the cleared ground, the clay that held its shape, the charcoal that held its record, the blue at the base of the flame, the orange that rises above it, the sphere that floats in silence where gravity cannot reach. All of it, part of the same quiet process. Transformation. Matter releasing what it holds, slowly and without hurry. And yet, the sun. The sun sits at the center of this solar system, burning, or so it seems, with a light so steady and so vast that it has guided every living thing that has ever existed on this planet. But the sun does not burn. Not in the way a candle burns, or a forest burns, or a piece of driftwood burns on a quiet beach. The surface of the sun reaches temperatures of about 5,500 degrees Celsius, far beyond anything a chemical fire can produce. And yet what happens there is something else entirely, something older and stranger than combustion. The sun fuses hydrogen. Deep in its core, hydrogen nuclei are pressed together under gravity so immense that they merge, becoming helium, releasing energy in the process. No oxygen required, no fuel in the way we understand fuel, no ash, no smoke, no charcoal left behind. It is not fire. It only looks like fire from here. True fire, the kind that crackles, that glows orange, that leaves a ring of ash in the morning, is a chemical event. Electrons rearranging themselves around atoms, releasing heat and light as they do. It requires oxygen. It requires a planet like this one. And for most of the universe's history, there was no such planet. There may still be no other planet quite like it. Fire, in the truest sense, may be one of the rarest things in the known universe, a process so particular in its requirements that it exists, as far as we can tell, only here. And even here, it had to wait. It had to wait for the right conditions to arrive. Lightning has always been one of the ways fire finds its beginning. Even now, lightning strikes the earth roughly 100 times every second. 100 times while you lie still. 100 times in the next second and the one after that. Each strike a brief channel of plasma, reaching temperatures far beyond any flame, lasting only a fraction of a moment before it is gone. And sometimes, where lightning meets dry grass or dry wood, fire begins. Volcanic eruptions have done the same throughout Earth's history. Lava meeting forest, or ash falling hot onto dry land. The planet itself offering ignition. But for most of Earth's early history, none of this produced fire as we know it, because there was nothing to burn. Or rather, there was not enough oxygen. The first land plants appeared and slowly, over millions of years, began releasing oxygen into the atmosphere as a byproduct of photosynthesis. The air thickened with it gradually, and somewhere around 420 million years ago, the oxygen reached a level sufficient to sustain combustion, and fire appeared on Earth for the first time. The evidence is there in the rock. Thin, dark layers of charcoal pressed between ancient stone, preserved across hundreds of millions of years. Geologists can read them the way you might read a diary. This layer, fire. This one, no fire. This one, fire again, and widespread. The planet had learned something new. And life, over the long stretch of time that followed, learned to live with it. More than that, some life learned to need it. There are trees alive today that cannot reproduce without fire. The giant sequoia, one of the largest living things on Earth, holds its seeds inside cones that may remain closed for 20 years or more. They wait, and when fire moves through the forest, the heat opens them. The cones release their seeds into soil that has just been cleared of competition, enriched by ash, open to sunlight. Without fire, the sequoia struggles to begin again. The lodgepole pine does something similar. Its cones are sealed with a resin that only melts at high temperatures. They're called serotinous cones, a word that comes from the Latin for late. They are cones that wait for the right moment, and the right moment is fire. In Australia, the relationship between plants and fire runs even deeper. Many species there have seeds that will not germinate at all without exposure to smoke, or to the specific chemical compounds that smoke carries. The seed lies dormant in the soil, patient, waiting for the signal that fire has passed and the ground is ready. Then, and only then, it begins. These are not accidents of evolution. They are adaptations, strategies shaped over millions of years of living alongside fire, life not merely surviving fire, but incorporating it, depending on it, using it as a clock, a signal, a key. The study of these relationships has its own name, fire ecology. It is the science of how fire shapes ecosystems over time, how it moves through landscapes, what it takes and what it gives back. And what it has revealed, slowly, is that fire is not simply a destroyer. It is also a maker. Fire releases nutrients locked inside dead plant matter and returns them to the soil. It clears the dense undergrowth that shades out smaller plants. It opens the canopy to light. In many ecosystems, a landscape that is not burned in a long time becomes, in a quiet way, less alive, less varied, less open, less able to support the full range of creatures that belong there. This is something that land managers have come to understand, sometimes slowly, sometimes only after watching what happens when fire is kept away for too long. In the 20th century, many countries adopted policies of fire suppression, putting out every fire as quickly as possible. The intention was protection. But over decades, the unburned fuel accumulated. Dry wood and dead brush built up across vast areas. And when fire eventually came, as it always does, it burned with an intensity that the landscape had never been designed to survive. The answer, in many places, has been to reintroduce fire deliberately. Controlled burns, sometimes called prescribed fires, are set carefully, under specific conditions, to reduce the accumulated fuel before it becomes dangerous. They are slow, managed, intentional. A fire that is invited, rather than one that arrives uninvited. It is, in a way, a return to something very old. Indigenous peoples on many continents had understood this for thousands of years. They burned landscapes deliberately, regularly, with knowledge passed down across generations, not to destroy, but to tend, to keep the land in a state that supported the plants and animals they depended on. Fire as a tool of care. Fire as something that, when understood and respected, gives back more than it takes. And so, the story of fire on this planet is not simply the story of destruction and danger. It is the story of a process woven so deeply into the fabric of life here that some living things cannot complete their own cycles without it. The sequoia cone, sealed and waiting. The Australian seed, lying still in the soil, listening for smoke. The lodgepole pine, patient in the cold, holding its resin until the moment arrives. All of them carrying, in their own way, the same long memory that you carry. A memory of fire as something necessary, something that clears the way, something that, in the end, makes room for what comes next. You are still now. The breath moves slowly. And somewhere, in a forest you will never visit, a cone is waiting for its moment. That cone is not alone in its waiting. Across the world, for as long as we can trace, people understood what the cone understood. That fire, given at the right moment, in the right place, is not an ending. It is an opening. Aboriginal Australians carried this knowledge for at least 50,000 years. 50,000 years of watching, learning, adjusting, reading the land the way you might read a face, noticing when it needed tending, when the grasses had grown too thick, when the old growth was crowding out the new. They called it cultural burning, and the word cultural is important. This was not simply a technique, it was a relationship, a set of responsibilities passed from one generation to the next, encoded in language and ceremony, and the quiet authority of those who had watched the land long enough to understand its rhythms. Other peoples on other continents held similar knowledge, in the Americas, in Africa, across parts of Asia and Europe. Deliberate burning was a form of conversation with the landscape, a way of saying, we are here, we are paying attention, and we know what you need. Then, in the 20th century, much of that conversation stopped. Fire suppression became policy. The idea, reasonable on its surface, was that fire was dangerous and should be prevented wherever possible. And so it was. Fought, contained, extinguished. Year after year, the fires that would have come did not come. And the fuel that those fires would have consumed stayed where it was, accumulating, quietly, season after season. The dry grass and the fallen branches and the dead wood built up across millions of hectares of land that had once burned regularly and gently. The land was not resting. It was loading. And when fire eventually returned, as it always does, it found more to burn than it had ever found before. The fires that followed were not the low, creeping fires that had shaped these landscapes for millennia. They were something else. A large wildfire, given enough fuel and enough wind, does not simply burn. It begins to behave like a living system. It generates its own weather. The heat rising from a major fire can push columns of smoke and air high into the atmosphere, high enough, under the right conditions, to form clouds. Not ordinary clouds. Pyrocumulonimbus clouds, fire-borne thunderheads that can reach the stratosphere itself. They carry the fire's energy upward into a part of the atmosphere that most weather never touches. And there, they do something that seems almost impossible. They produce lightning that travels outward from the storm, striking the ground kilometers, sometimes tens of kilometers from the original fire, starting new fires. The blaze, in a sense, reaching beyond itself, seeding its own continuation across the landscape. Fire tornadoes can form in the intense heat gradients near a large burn, columns of rotating flame, sometimes dozens of meters tall, moving unpredictably across the ground. They are not metaphors. They are real atmospheric structures, born from the same physics that produces ordinary tornadoes, but fed by combustion. The smoke from these fires does not stay local. It rises, and the wind takes it. The smoke from a large wildfire in one part of the world can travel thousands of kilometers within days, crossing oceans, settling over cities on other continents, turning the light a strange amber color that people notice without always knowing why. the air carrying within it the chemical signature of a forest they have never seen. That smoke is not simply particles of carbon, it is a complex mixture. Fine particulate matter, small enough to pass through the nose and throat and settle deep in the lungs. Carbon monoxide, colorless and odorless. A gas that finds its way into the blood and binds to hemoglobin more readily than oxygen does, displacing the oxygen quietly, without announcement. And alongside these, hundreds of other compounds, volatile organic molecules, nitrogen oxides, traces of metals and resins, each one a remnant of something that was once alive and is now dispersed into the air. The smallest soot particles are among the tiniest solid objects that enter the human body, smaller than a bacterium, small enough to cross from the lungs into the bloodstream. The body, which evolved to handle the modest smoke of a small hearth fire, was not designed for the scale of what large industrial or wildfire smoke can carry. And some fires do not rise at all. Some fires go down. Peat is ancient compressed plant matter, the accumulated remains of mosses and sedges and grasses laid down over thousands of years in waterlogged ground. It holds an enormous amount of carbon, and it burns, slowly, without flame, smoldering through the organic layers underground. A peat fire can persist for months, for years. It can burn through winter, beneath snow, invisible from the surface, moving through the ground at its own quiet pace, waiting for conditions to change, waiting for the surface to dry again. There is a coal mine in a small town in Pennsylvania called Centralia. In 1962, a fire reached an exposed coal seam beneath the ground, and it has been burning ever since. For more than 60 years, the fire has moved through the coal deposits underground, slowly, steadily, with no intention of stopping. The town above it was largely abandoned. The roads cracked and subsided. Steam rose from fissures in the earth, and the fire continued, indifferent to the decades passing above it. Centralia is unusual only in that it is known. Natural coal seam fires exist on every continent, burning in remote mountains, in desert badlands, in places where no one lives to notice the smoke rising from the hillside. Collectively, they release a significant amount of carbon dioxide into the atmosphere each year. Fires that no one lit, that no one tends, that have in some cases been burning for centuries. Fire, wherever it burns, produces carbon dioxide and water vapor as its primary outputs. The carbon that was locked inside the wood, or the coal, or the peat. Carbon that was once pulled from the atmosphere by living plants, sometimes long ago, is returned, released back into the air as gas. The fire is, in this sense, a kind of reversal, a slow undoing of the work that photosynthesis once did. Carbon that spent years or decades or millennia in solid form, moving again. When combustion is incomplete, when there is not quite enough oxygen, or the temperature is not quite high enough, the carbon does not fully oxidize. Instead of carbon dioxide, it becomes carbon monoxide. One carbon, one oxygen instead of two. A small difference in chemistry that carries large consequences for any living thing that breathes it in. And the soot, the fine, dark particles that rise from every fire, that settle on every surface downwind. They are the visible record of combustion that did not quite finish. Carbon that almost became gas, but remained, instead, as solid, drifting. You breathe slowly now. The body knows, without being told, that the air around you is clear, that the warmth you feel, if you feel any, is safe, that the darkness is simply the darkness, and the night is simply the night. Somewhere, deep in the ground, old fires continue their patient work, and somewhere above, the atmosphere holds within it the faint chemical memory of 1,000 distant burns, all of it part of the same long cycle. Carbon moving, always moving, between the living world and the air and the earth, and back again. And for most of human history, that carbon, that smoke, had nowhere to go. For tens of thousands of years, fire lived inside human dwellings without any means of escape. The hearth sat at the center of the room, and the smoke simply rose and spread and settled, filling the space where people slept and ate and breathed. It is difficult now to imagine what that was like. The walls of ancient homes were dark with it. The lungs of the people who lived there carried it. Chronic cough, irritated eyes, shortened breath. These were simply the conditions of a life lived close to fire. The price of warmth. Then, sometime in medieval Europe, someone built a hole in the wall above the fire, a channel, a chimney, and the smoke had somewhere to go. It seems like such a small thing, a vertical passage through stone or brick, but the chimney changed the quality of indoor air more dramatically than almost any other architectural invention. It separated the fire from the breath. It allowed people to have warmth without the slow accumulation of harm. The air inside a home became, for the first time, something close to clean. And yet, in many parts of the world today, that separation has not happened. Open cooking fires still burn inside enclosed spaces, without ventilation, without chimneys. The smoke still rises and spreads and settles. The same chronic exposure that marked ancient life continues, quietly. In the present, it is one of the more significant sources of indoor air pollution on Earth, and it falls most heavily on those who spend the most time near the fire, often women, often children. The body has not forgotten what smoke means. Even now, even here, in a room with clean air and no fire burning, the nose remains alert to it. The human sense of smell can detect smoke at concentrations of just a few parts per million, a trace so faint it would be invisible to any instrument you could hold in your hand. And yet, the nose finds it. This sensitivity is almost certainly ancient, older than language, older than tools, older perhaps than the species itself. The ability to smell smoke at a distance, to know that fire was near before it became dangerous, would have been worth everything to an early human moving through a dry landscape, worth survival. Smoke detection may be one of the oldest instincts still running in the human sensory system. A quiet alarm, always on, waiting for a signal that almost never comes anymore. But there is another side to fire's relationship with the human body, one that moves in the opposite direction from alarm. When the fire is contained, when it is small and warm and near, something else happens. Researchers have studied what occurs in the body when a person simply watches a fire, not a recording, not a photograph, an actual fire burning. And what they found was a measurable drop in blood pressure, systolic pressure. The higher of the two numbers fell as participants watched the flames, and the longer they watched, the greater the reduction. There was a dose in it, more fire, more calm, as if the body were receiving something it had been waiting for. The explanation most researchers offer is evolutionary. For 1 million years or more, the sight of a controlled fire meant safety. It meant the group was together, the perimeter was lit, the cold was held at bay. The predators that feared fire were somewhere beyond the light, and the people were here, inside it, warm. The nervous system learned, over all that time, what a fire at close range means. It means rest is possible. It means the vigilance can soften. And so, even now, even in a body that has never spent a night in the open, the old signal still arrives. The blood pressure falls, the shoulders drop, the breath slows. You may feel something like that now. The crackling of a fire carries its own quiet message. Each small pop is the sound of water vapor, trapped inside the wood, in tiny pockets within the grain, expanding suddenly as the temperature rises. The wood holds moisture even when it seems dry, and as it burns, that moisture becomes steam, and the steam pushes outward faster than the wood can yield, and the sound escapes. A crack, a soft pop, a low, irregular percussion that follows no pattern and repeats no rhythm. That irregularity may be part of why it soothes. The human nervous system is alert to patterns, to repetition, to signals that carry information. But the crackling of a fire carries none. It is random in the way that rain is random, in the way that wind through leaves is random. The brain listens for a moment, finds nothing to decode, and releases its attention. The specific quality of those sounds, low in frequency, irregular in timing, may overlap with something the nervous system already knows how to receive, not as a signal, but as a texture, a background that asks nothing. And the light. A flame does not hold still. It shifts and bends and brightens and dims in cycles too complex to follow. The frequency of that flickering, the rate at which a candle or a campfire pulses, falls within a range that overlaps with certain brainwave patterns. The patterns associated with relaxed alertness, with the mind that is awake but not straining, present but not searching. Whether the flicker causes that state or simply accompanies it is not entirely settled, but the overlap is there. The fire moves at a frequency the resting brain already knows. And the warmth. The heat from a fire travels primarily as infrared radiation, long wavelengths, invisible to the eye, that pass through the air and meet the skin and press slightly inward, not just warming the surface, but reaching a little deeper. The sensation is different from the warmth of a heated room. It has direction and weight, and a quality that is sometimes described as reaching into the body rather than simply surrounding it. The skin receives it. The muscles beneath it soften slightly. The body interprets it, perhaps, as the warmth of proximity, of being close to something that means safety. Of all the animals on Earth, only one has ever learned to make this happen deliberately. Only one has gathered fuel and struck a spark and coaxed a small flame into being and tended it through the night. Every other creature that has ever warmed itself by fire has done so by accident, by finding what was already burning. Only the human hand has made fire where there was none before. That is not a small thing. It is, in some ways, the oldest expression of what the human mind can do. The ability to look at the world and see not only what is, but what could be. To see a dry stick and a stone and understand, somehow, that warmth is waiting inside them. And now, after 1,000,000 years of tending that warmth, after 1,000,000 years of sitting beside it as the dark gathered and the night deepened and the body finally let itself rest, the signal is still there. The warmth, the flicker, the soft, irregular sound of something slowly, gently burning. The body knows what to do with it. It has always known. And yet, humans are not entirely alone in this. Not quite. There are birds in the dry savannas of northern Australia that have been observed doing something that stops researchers mid-sentence when they describe it. Black kites, whistling kites, brown falcons. These birds have been seen picking up smoldering sticks at the edge of a wildfire, carrying them in their beaks or talons, and dropping them deliberately into unburned grass some distance away. The grass catches, small animals flee the new flames, and the birds are waiting. It is called fire hawking. And it is, as far as anyone can tell, the closest any non-human animal has come to using fire as a tool. Not making fire, not maintaining it, but carrying it, redirecting it, understanding, in some way, that fire moves things. The behavior has been reported by Aboriginal Australians for generations, long before Western scientists began documenting it. It is still debated in the scientific literature. The evidence is observational, gathered from field accounts rather than controlled study. But the accounts are consistent, and they come from multiple independent sources across a wide geographic area. So the picture that emerges is this. One species learned to make fire from nothing. A few others learned, in their own way, to use what was already burning. And every other creature on Earth, the hundreds of thousands of species that have lived alongside fire for hundreds of millions of years, has simply moved away from it, or toward it, cautiously, for warmth, but never with intention. Fire, as a deliberate act, belongs almost entirely to one lineage. And perhaps that is why the human relationship with fire is so layered, so old, so quietly complicated. The fear of it is real. A small number of people experience genuine pyrophobia, a deep, persistent dread of flames that goes beyond ordinary caution. It is relatively rare. Far more common is the opposite: a pull toward fire, a tendency to sit closer than necessary, to watch longer than makes practical sense, to find the eyes drifting back to a candle flame, even in the middle of a conversation. This mild attraction has a name in the clinical literature: pyrophilia, in its benign form, and it is considered entirely normal, not a disorder, not an anomaly, but a trait, something woven into the ordinary human response to fire. Which makes a certain kind of sense. If your ancestors spent 1,000,000 years gathering around flames each evening, if the fire was where food was prepared, where warmth was found, where the group came together and the stories were told, then a quiet draw toward firelight is not strange at all. It is memory, written not in words, but in the nervous system itself. The body leans toward what kept it alive. And so, for most of human history, the question was not whether to have fire, but how to make it. How to call it into being from the cold, indifferent world. The oldest method we know of, or at least the oldest we can reconstruct with confidence, involves friction. A wooden spindle pressed into a hearthboard and rotated rapidly between the palms. The bow drill made this easier, using a looped cord to spin the spindle faster and more consistently than bare hands alone could manage. The heat builds slowly. A thin curl of smoke rises from the notch in the board. And if everything is right, if the wood types are matched correctly, the spindle neither too hard nor too soft relative to the hearthboard, the resin content compatible between the two, a small dark coal forms in the notch. That coal is transferred, with great care, to a bundle of dry tinder, cupped in the hands and gently, steadily blown. The tinder glows, then catches. It is a process that requires patience and knowledge and a kind of attentiveness that is almost meditative. The variables are many: humidity, wood species, the angle of the notch, the steadiness of the pressure. A person who can reliably make fire this way has spent a long time learning how. There is another method, older in some traditions, that works on an entirely different principle. Flint struck against steel or against iron pyrite fractures tiny particles of iron from the surface. Those particles, superheated by the impact, oxidize almost instantly in the air. They are, for a fraction of a second, burning. A spark. Directed onto tinder, that spark can become a fire. It is a faster method than friction in skilled hands, but it still requires the right materials, the right tinder, the right conditions. And then there is the fire piston, a device used in parts of Southeast Asia, elegant in its simplicity. A small cylinder, sealed at one end, with a tight-fitting plunger. A piece of tinder placed at the closed end, and then the plunger driven in sharply. The air inside has nowhere to go. It compresses in an instant, and compression generates heat, enough heat, if the stroke is fast enough, to ignite the tinder. No spark, no friction, just the physics of a gas under sudden pressure. It is a reminder that fire can be reached by more than one path, that the principles underlying it, heat, fuel, oxygen, can be assembled in different sequences through different means. For most of human history, making fire was a skill, something learned, practiced, passed down. Then, in the early 19th century, something changed. The match arrived. A small stick tipped with a chemical compound that would ignite with a single stroke against a rough surface. It replaced flint and steel almost everywhere within a few decades. The ability to make fire, which had required knowledge and practice and the right materials, became something a child could do. The early matches were not without their dangers. Phosphorus, white phosphorus, used in the first generations of friction matches, is deeply toxic. Factory workers who spent their days handling it developed a condition that came to be known as phossy jaw, a slow, agonizing destruction of the jawbone caused by phosphorus poisoning. It was one of the industrial era's quieter horrors, largely invisible to the people who bought the matches and struck them without a second thought. The safety match, developed in Sweden in 1844, addressed this by separating the reactive chemicals. The match head and the striking surface each contained only part of what was needed. Neither could ignite alone, only together. In the act of striking, did they complete the reaction? It was a small but meaningful piece of engineering. Fire made safer by being made incomplete until the moment it was needed. And there is one more detail worth holding quietly for a moment. The lighter came before the match. An early version, using hydrogen gas, was created in 1823, more than a decade before the safety match was developed. The history of fire-making tools does not move in a straight line from simple to complex. It moves in loops, in parallels, with different inventors in different places solving the same ancient problem by different means. All of them reaching, in their own way, toward the same thing. A small, controlled flame. The same thing a hominid reached for 1 million years ago in a cave in South Africa. The same thing the birds of northern Australia reach for, in their own way, when they carry a burning stick across the savannah. The same thing the body reaches for, even now, when it finds itself drawn toward a candle on a quiet evening and simply watches. The flame does not ask to be understood. It only burns, steadily, softly, the way it always has. And yet the flame holds more information than it first appears to give. Look closely at the color of a fire, not just the orange and yellow of its outer mantle, but the specific hues that different materials produce when they burn. Each element, when heated to the point of combustion, releases light at its own particular wavelengths. Copper burns green, sodium burns yellow, potassium burns a soft violet. These are not accidents of perception, they are signatures, each element announcing itself through light the way a voice announces itself through sound. The flame is ear, in this sense, a kind of language, one that chemists learned to read long before they had other tools to work with. This is the same principle behind fireworks. The colors in a night sky are not painted on, they are chosen through chemistry. Strontium salts produce red, barium produces green, magnesium burns white, intensely, almost painfully bright. Each burst of color is a controlled combustion, timed and composed the way a piece of music is composed, with specific elements assigned to specific moments. It is a long way from a burning stick in a cave, and yet the impulse is recognizable. Fire, made beautiful on purpose. Fire, shaped by human hands into something that rises and opens against the dark. The temperatures involved in all of this vary more than most people realize. A wood fire, the kind that has warmed human bodies for 1 million years, burns at roughly 600 to 900 degrees Celsius. That range depends on the wood, the airflow, the stage of the burn. A fire just catching holds less heat than one that has been burning steadily for an hour. But somewhere in that range, wood becomes light and warmth and ash. A candle flame, small as it is, reaches roughly 1,000 degrees Celsius at its hottest point, the blue zone near the base, where combustion is most complete. It is a quiet thing to hold in mind that a single candle, the kind that fits in the palm of a hand, contains within it a point of heat that would destroy almost any organic material it touched. And yet it sits there, steady, contained, casting just enough light to read by. Move further along the scale, and the numbers become harder to hold as images. An acetylene torch reaches temperatures above 3,500 degrees Celsius, hot enough to cut through steel, hot enough to melt most metals as though they were wax. This is fire pushed to an extreme, fire concentrated and directed, fire as a precision instrument. And then there is lightning. The surface of a lightning bolt reaches approximately 30 000 Kelvin? That is not a misreading. It is roughly 5 times hotter than the surface of the sun. A bolt of lightning, lasting a fraction of a second, achieves temperatures that no ordinary fire approaches, that no furnace approaches, that almost nothing on Earth approaches. At those temperatures, matter behaves differently. The gas inside a lightning bolt is not simply hot air. It is plasma, the fourth state of matter, in which electrons are stripped from their atoms entirely, leaving a charged, luminous channel of ionized gas. Plasma is present in lightning. It is present in the sun. It is present in the stars. It is not present in ordinary fire. Fire is sometimes described as a plasma, and the description is understandable. Fire glows. Fire conducts some electricity. Fire behaves in ways that seem to blur the boundary between states of matter. But technically, fire lacks the ionization density to qualify. The electrons in a flame are not stripped free the way they are in true plasma. Fire sits at the edge of that category, close enough to invite the comparison, but not quite crossing the threshold. It is, in the end, its own thing. Not solid, not liquid, not gas, not plasma. A process, not a substance. A reaction wearing the appearance of a presence. And perhaps that is part of why it has always seemed to humanize, like something more than chemistry. The word for fire in Proto-Indo-European, the ancient reconstructed language that gave rise to most of the languages of Europe and parts of Asia, is something close to peyor. It is one of the oldest recoverable words in the human linguistic record, older than writing, older than agriculture, a sound that people made somewhere on the Eurasian steppe, thousands of years before any of the civilizations we know by name. They had a word for it, which means they thought about it enough to name it, which means it mattered. Fire appears in the mythology of nearly every human culture, and in a remarkable number of those myths, fire is not something humans discovered. It is something they received, or stole, or were given as a gift from somewhere beyond the ordinary world. The Greek myth of Prometheus is perhaps the most familiar version of this story, a titan who took fire from the gods and brought it down to human beings, and was punished for it severely. The myth does not present fire as a simple tool. It presents it as something that belonged elsewhere, something that had to be taken at great cost, something that changed the nature of human life irrevocably. That intuition, that fire is extraordinary, that it comes from somewhere beyond the merely human, appears in cultures that had no contact with ancient Greece. It surfaces in stories from the Americas, from sub-Saharan Africa, from the Pacific Islands. The details differ. The feeling is the same. Something was given or taken, and nothing was the same afterward. In many traditions, fire carries a meaning that extends beyond warmth and light. It is associated with purification, the idea that passing through fire or through smoke cleanses something that ordinary water cannot reach. It is associated with transformation, the way fire changes everything it touches into something else, something that cannot be changed back. And it is associated with the boundary between the living and the dead. Funeral pyres, sacred flames kept burning at the threshold of temples. The idea that fire accompanies the soul on its passage from one state to another. These associations are not arbitrary. They arise from observation. Fire does transform. It does consume. It does mark the end of one thing and the beginning of something else. The eternal flame is a symbol that appears across cultures and across centuries. In ancient Greece, sacred fires were kept burning continuously at certain sites, tended by priests or priestesses whose only task was to ensure the flame did not go out. In modern times, eternal flames burn at war memorials and state monuments on nearly every continent. The symbol has traveled through thousands of years of human history without losing its meaning. A flame that does not go out, a light that persists through darkness, through weather, through the passage of time. It stands for something that human beings have always wanted to believe in, that some things endure, that some things, once lit, are not easily extinguished. There is something very old in that feeling. Older than the myths that carry it, older than the words used to describe it, as old, perhaps, as the first hominid who sat beside a fire in the dark and felt, without being able to say why, that the flame was worth protecting, that it should not be allowed to go out. Zoroastrianism carries this feeling into formal theology. It is one of the oldest religions still practiced on earth, and at its center, tended and honored, is fire, not as a god itself, but as a symbol of truth, of divine light, of the clarity that burns away what is false. Zoroastrian fire temples have kept flames burning continuously for centuries. Some of those fires, it is said, have not been extinguished in over 1,000 years. The same impulse that moved an early hominin to protect a flame in the dark found its way, eventually, into sacred architecture, into ritual, into theology. Fire has been used in religious ceremony on every inhabited continent. Everyone. Across cultures that never contacted each other, across languages with no common root, across belief systems that agree on almost nothing else, fire appears at the center of the sacred. It marks birth and death. It purifies and consecrates. It carries prayers upward in smoke. It illuminates the darkness at the threshold of the holy. There is something in that convergence worth sitting with quietly, that so many separate human minds in so many separate corners of the world looked at the same phenomenon and felt the same thing, that this was not ordinary, that this deserved reverence. Perhaps they were right. The Olympic flame is another thread in this long weaving. The tradition traces back to ancient Greece, where fire was kept burning at sacred sites as a continuous presence, not lit for an occasion and then extinguished, but maintained, tended, kept alive as a kind of permanent witness. The modern Olympic flame carries an echo of that practice. It is lit in Olympia, in Greece, using a curved mirror to focus sunlight, fire drawn down from the sky itself, and then carried by relay across whatever distance separates that origin from wherever the games are held. The flame travels through human hands, passed from one to the next, never touching the ground, never going out. It is a very old idea, dressed in modern ceremony. And then, at some point in human history, the relationship with fire shifted. It had always been a tool for warmth, for light, for cooking, for protection. But somewhere around 5,000 to 6,000 years ago, people began to use fire in a new way. They began to use it to change the nature of matter itself. Copper smelting. Someone, somewhere, we do not know exactly where or when, discovered that certain stones, when heated intensely enough, would yield a soft, workable metal, copper. The first metal that human hands shaped deliberately. It required fire far hotter than a cooking fire, sustained, controlled, directed heat. But once achieved, it opened something entirely new. A material that could be cast into shapes, sharpened, repaired, reused. Then came bronze. Bronze is an alloy, copper and tin, melted together in precise proportion. It is harder than copper alone, holds an edge better, lasts longer. But it required fire hot enough to melt both metals simultaneously, and the knowledge to combine them in the right ratio. This was not accidental. This was accumulated understanding, passed down through generations of metalworkers who had learned, through long practice, what fire could do when it was given the right conditions. The Bronze Age reshaped civilization. Tools, weapons, vessels, ornaments, all of it made possible by the controlled application of heat to stone and metal. Fire had fed the human brain, and now the human brain was teaching fire new tasks. Iron came later, and it was harder to reach. Iron smelting requires temperatures above 1200 degrees Celsius. That is not achievable with an ordinary fire burning in open air. It requires forced air, bellows driving oxygen into the furnace, raising the temperature beyond what natural convection can produce. The blast furnace, developed in medieval China and later in Europe, used exactly this principle. Bellows, driven by hand or by water wheel, pushed air into the burning chamber, and the fire responded by climbing to temperatures that could reduce iron ore to liquid metal. The iron that came out of those furnaces built the medieval world. Plows, bridges, armor, tools of every kind. All of it descended from the insight that fire, given more air, becomes something more than fire. But all of this required charcoal. Charcoal is wood that has been burned slowly in a low oxygen environment. The process drives off water and volatile compounds, leaving behind almost pure carbon. That carbon burns hotter and cleaner than raw wood. It was essential to early metallurgy, the fuel that made the temperatures possible. And the demand for charcoal was enormous. Forests across Europe and Asia were consumed to feed the furnaces. Hillsides that had been wooded for thousands of years were stripped bare. The hunger of the forge reshaped landscapes on a continental scale. It is a quieter kind of consequence than a wildfire, but no less real. Then, in the 18th century, coal began to replace charcoal as the primary industrial fuel. Coal burned hotter, was available in vast quantities underground, and did not require the slow conversion of living wood. And with coal came something that changed the world more profoundly than bronze or iron had: the steam engine. For the first time in history, fire became motion. Not the motion of a person carrying a torch or a flame spreading across dry grass, but mechanical motion, sustained and controllable, driving pistons and wheels and pumps. The heat of burning coal turned water to steam, and steam pushed against a piston, and the piston turned a shaft, and the shaft drove a mill, a loom, a locomotive. Fire, which had always released its energy as heat and light, was now being converted into work. The Industrial Revolution was, at its core, a new relationship between fire and human intention. That relationship kept deepening. The internal combustion engine took the same principle and made it smaller, faster, more precise. Fuel burns inside a cylinder. The rapid expansion of hot gas pushes a piston. The piston turns a crankshaft. Motion, again, but now compact enough to fit inside a vehicle, to move a person from one place to another at speeds no animal could sustain. And then the jet engine. Fuel burns continuously in a controlled stream. The hot gases expand and rush backward with tremendous force, and by Newton's third law, the engine, and everything attached to it, is pushed forward. A tube of controlled fire moving through the sky. Each of these is fire, the same fundamental process, fuel combining with oxygen, releasing energy that warmed the first human hands around the first controlled flame. The same reaction that cooked the first meal, that hardened the first spear tip, that lit the first cave painting. Only the scale has changed, only the precision, only the application. The fire itself is the same. Rapid oxidation, heat and light released, matter transformed. It has been doing this, in one form or another, for as long as there has been oxygen on this planet, long before there were hands to tend it, long before there were eyes to watch it. And here, in the quiet of this moment, it is still doing it somewhere. A candle burning down in an empty room, a hearth cooling to embers in a house where everyone has gone to sleep, a forest fire moving slowly through the dark, miles from the nearest road. Fire does not rest. But you can. And somewhere beyond all of that, beyond the jet stream and the stratosphere and the thin blue line where atmosphere fades into nothing, fire still burns. Rocket engines carry their own oxygen with them, sealed inside tanks, compressed and waiting. Because out there, in the vacuum between worlds, there is no atmosphere to draw from, no air to feed a flame. So the fuel and the oxidizer travel together, and when they meet inside the combustion chamber, they burn. A controlled, continuous fire in a place where fire has no right to exist. And what does that fire leave behind? When hydrogen and oxygen burn together in a rocket engine, the exhaust is water vapor. Only that, a cloud of steam, dispersing silently into the void. The most destructive seeming thing, a column of fire powerful enough to lift hundreds of tons off the ground, and what it releases into space is simply water. There is something quietly remarkable in that. The same two elements that make up the oceans, combining, burning, and returning to themselves. Fire has not always been used so gently. For as long as humans have understood fire, they have also understood its power to destroy, and they have used it. In warfare, fire was a weapon long before gunpowder, long before iron. Burning arrows, burning ships, burning fields. The intention was always the same, to take the thing that warms and feeds and turn it toward ruin. Among the most feared incendiary weapons in history was a substance known as Greek fire, developed by the Byzantine Empire sometime in the 7th century. It could be projected from ships through bronze tubes, a stream of burning liquid that spread across the surface of the water and kept burning. It could not be extinguished with water. It may have burned more intensely when water was applied. Entire naval battles turned on it. Fleets were destroyed by it. Enemies who had never seen it described it with something close to awe. And then, it was lost. The exact formula of Greek fire was never written down in a way that survived. Or if it was, those records did not reach us. The Byzantine Empire fell, and the secret went with it. Historians and chemists have proposed many reconstructions: quicklime, naphtha, pine resin, various combinations, but none has been confirmed. It remains one of the few genuinely unsolved chemical mysteries of the ancient world. A weapon so effective that its makers kept it secret, and kept it so well that even they, eventually, forgot. The 20th century found its own answers to the same problem. Napalm is a thickened fuel, a gel that clings to whatever it touches and burns at extremely high temperatures. It does not splash and scatter like liquid. It adheres. It was developed during the Second World War and used in conflicts across the following decades. Its properties made it effective and, for the same reasons, terrible. These are not comfortable facts. They sit alongside the warmth of the hearth and the light of the cave painting and remind us that fire has always been both things at once: the gift and the danger, the tool and the weapon. It has never been only one. Let the mind move away from that now and outward into the larger picture. Every year, fire burns across roughly 3 to 4 million square kilometers of the Earth's surface. That is an area larger than India. Forests, grasslands, savannas, scrublands, burning in cycles that have continued for hundreds of millions of years. And when they burn, they release carbon that was pulled from the atmosphere by plants over years and decades and centuries, locked into wood and root and leaf. Fire unlocks it again, returns it to the air as carbon dioxide, and the cycle continues. This is not only destruction, it is a kind of planetary breathing. Carbon moving from the atmosphere into living things, and from living things back into the atmosphere. Fire is one of the oldest mechanisms in that exchange. It was doing this long before humans arrived to watch it. Since the 1990s, satellites have allowed scientists to observe this process from above. In near real time, instruments in orbit detect the heat signatures of fires burning across every continent. They map the smoke, trace the spread, measure the area consumed. What was once invisible, the full scale of global fire, became, for the first time, something that could be seen all at once. And what the satellite showed was that fire is not an exception. It is a constant. Somewhere on Earth, at almost any moment, something is burning. But there are quieter ways to read fire's history. Inside the rings of old trees, there are scars. When a fire passes through a forest and a tree survives, it leaves a mark in the wood. A narrow band of darkened, damaged tissue that the tree grows around in the years that follow. Dendrochronologists, scientists who study tree rings, can read these scars the way others read written records. They can say, a fire passed here in this year, and again here, and here, reconstructing centuries of fire history from the silent testimony of wood. Some trees have dozens of these scars, a life spent in a landscape where fire came and went and came again, and the tree endured. The ponderosa pine is one of those trees. Its bark grows thick and deeply furrowed over time, almost like armor. Low-intensity fires move through the forest floor, and the ponderosa stands above them, scorched at the base but alive. It has been doing this for a very long time, adapting not to avoid fire, but to coexist with it. There is a kind of patience in that, a long, slow accommodation with something that cannot be stopped. And in the aftermath of fire, life returns, sometimes within hours. The black-backed woodpecker does not wait long. It is drawn to recently burned forests, where the standing dead trees, called snags, are full of wood-boring beetle larvae. The woodpecker moves through the blackened trunks, methodical and unhurried, finding food in the wreckage that other birds cannot reach. It nests in the charred wood, raises its young there. The burned forest is not a wasteland to the black-backed woodpecker. It is exactly the right place. And the insects arrive even sooner. Within hours of a wildfire, certain beetles and flies are already moving toward the smoke, drawn by the heat, by the infrared radiation, by chemical signals in the air. They have evolved specifically for this moment, the brief window after a burn when the wood is fresh and the competition is low. They do not flee from fire, they follow it. Life does not simply recover from fire. In many cases, it was waiting for it. And so the picture that emerges, if you hold it all together quietly in the mind, is not one of destruction and recovery. It is something more continuous than that. Fire and life, moving together through time, each shaping the other. The trees growing thicker bark, the birds learning to follow the smoke, the beetles reading infrared from 80 kilometers away. All of it woven into a single, slow process. That has been unfolding for longer than there have been eyes to see it. And within that process, there are details so precise they feel almost like intention. The Melanophila beetle does not simply sense heat in a general way. It carries, on the underside of its thorax, two small pit organs, each containing a cluster of sensory cells that respond specifically to infrared radiation, the kind of radiation that a burning forest emits from as far as 80 kilometers away. 80 kilometers. The beetle feels the fire before it could ever see it, before the smoke has reached it, before any other signal has crossed the distance. It turns, and it flies toward the warmth, not away from it. And when it arrives, it finds freshly burned wood, still warm, still soft, and it lays its eggs there. The larvae will hatch into a world with almost no competition. The other insects that might crowd them out have not yet returned. The predators that would hunt them have not yet moved back in. The burned wood is not a hostile place for Melanophila. It is the safest place it knows. This is what millions of years of coevolution with fire looks like. Not avoidance, but precision. A creature so finely tuned to fire's aftermath that it can read the infrared signature of a burning forest from the distance of a small country. And the beetles are not alone in this. In the months after a fire, something else begins to happen beneath the surface of the soil. Fungi that have been waiting, sometimes for years, begin to fruit. They push up through the ash, through the blackened earth, into the open air. Fungi that appear almost nowhere else, that seem to require the particular chemistry of a burned landscape to complete their life cycle. Among the most well-known of these is the morel. In spring, in the months following a forest fire, morel mushrooms emerge from burned ground in numbers that can seem almost impossible, pale and ridged with their strange honeycomb caps, rising from the ash as if the forest were already beginning to remember what it was. The exact mechanism is still not fully understood. It may be that fire alters the soil chemistry in ways that trigger germination. It may be that the heat kills competing organisms, giving the morel's mycelium room to expand. It may be something else entirely. As with so much in fire ecology, the full picture is still being assembled. But the morel has been fruiting in burned forest for a very long time, long before anyone was there to notice it. And beneath the mushrooms, something simpler is also happening. Fire releases nutrients. When plant matter burns, the complex organic molecules that held carbon, nitrogen, phosphorus, and other elements in their structure are broken apart. Those elements return to the soil in simpler forms, more immediately available to roots, to fungi, to the next generation of plants. The ash is not empty. It is, in a sense, concentrated. And so in the weeks and months after a fire, there is often a surge of growth. Grasses pushing up through the black ground, wildflowers appearing in burned clearings, plants that had been suppressed by shade suddenly finding light. The landscape does not simply recover. It responds. It takes what the fire left behind and builds with it. This is most visible in grasslands. Grasslands that burn regularly, whether from lightning or from the deliberate fires of the people who have managed them for thousands of years, tend to carry more species than grasslands where fire has been kept out. More varieties of grass, more wildflowers, more insects, more birds. The suppression of fire, over time, allows a few dominant species to crowd out the rest. Fire resets the balance. It opens the canopy, clears the accumulated thatch, returns the nutrients, and gives the smaller, slower, less competitive species a chance. This is not a recent discovery. It is something that land managers and ecologists have been documenting for decades, and something that indigenous peoples understood long before that. And at the largest scale, fire does not just maintain grasslands. In many parts of the world, it creates them. The savanna, that vast, open landscape of scattered trees and long grass that covers much of Africa, large parts of South America, and significant areas of Australia, exists, in part, because of fire. Without periodic burning, many savannas would gradually close. The trees would grow denser, their canopies would meet, the grasses would thin and disappear in the shade, and what had been open savanna would become closed forest. Fire keeps the trees from winning. It is a slow negotiation, played out over seasons and centuries. The grasses grow, accumulate, dry. A fire moves through. The trees are set back. The grasses return, and the savanna persists. This relationship is not new. The grasses and the fires and the open landscapes have been moving together for tens of millions of years, long before the animals that now graze those plains had evolved, long before the first hominins stood upright in the African grassland and looked out across the horizon. The savanna that shaped our ancestors was itself shaped by fire. There is something worth holding quietly here. The landscape in which human beings first became human was a landscape that fire had made and continued to make, season after season, for longer than the mind can easily hold. And yet fire is not the only thing that makes light in the dark. There are other kinds of light, older in some ways, stranger, that have nothing to do with combustion at all. Bioluminescence is the production of light by living organisms through chemical reactions that generate almost no heat. It is found in fireflies, in deep-sea fish, in certain jellyfish, in plankton that make the ocean glow blue when disturbed at night. It is sometimes called cold fire because it shares fire's quality of light without fire's quality of heat. In forests, on the forest floor, on the surface of rotting logs, there is a faint and quiet version of this. Foxfire. Certain fungi, as they grow through decaying wood, produce a soft bioluminescent glow, pale greenish white, barely visible except in complete darkness. It has no known purpose that science has fully explained. It may attract insects that help disperse spores. It may be a byproduct of the chemical reactions involved in breaking down wood. It may be something else. But it glows quietly in the dark forest, on the wood that is slowly returning to soil. People have noticed foxfire for a very long time. It appears in old accounts of forests and marshes described as an eerie light with no source, a glow that did not burn. And there is another light that carries fire's name without fire's nature. St. Elmo's fire. During thunderstorms, on the tips of ship masts, on the points of church spires, on the horns of cattle standing in open fields, a faint blue or violet glow sometimes appears. It flickers and hisses. It looks, to anyone who has not seen it before, like something burning. But it is not fire. It is plasma, a corona discharge, the result of the strong electric fields that build up during a storm ionizing the air around a sharp point. It produces light. It produces a faint crackling sound, but it produces almost no heat, and it cannot ignite anything. St. Elmo's fire is fire only in name. It is electricity wearing fire's appearance, a reminder that light and heat and flame are not always the same thing, that the word fire reaches further than the phenomenon. And there are other lights that have carried fire's name through the centuries. Lights seen hovering over marshes and bogs at night, drifting just above the surface of still water, flickering as if alive, moving, sometimes as though they were leading someone somewhere. Will-o'-the-wisps. People have tried to explain them for a very long time. Some said they were spirits, the souls of the restless dead, lanterns carried by mischievous beings who lured travelers off safe paths and into the dark water. The explanation that has emerged from science is quieter than any of those stories, but no less strange. Beneath the surface of a marsh, organic matter decays slowly in the absence of oxygen. That process produces gases, methane, and a compound called phosphine. Phosphine can ignite spontaneously when it meets the air, and when it does, it may briefly ignite the methane around it, producing a small, pale, drifting flame. A flame with no fuel you can see, no hearth, no wood, just a soft light above the water, burning for a moment and then gone. Fire, appearing on its own, out of the slow work of decay. It is a reminder that combustion does not require human hands, that the conditions for fire exist quietly in the world, waiting. And yet, there is a boundary to what fire can be. Fire is a chemical process. It is electrons rearranging themselves as molecules break apart and recombine, releasing energy as they do. That energy becomes light and heat. It is, in the end, a surface phenomenon happening at the level of atoms bonding and unbonding. The sun does something entirely different. The sun converts roughly 600 million tons of hydrogen into helium every second, not by burning it, but by fusing it, pressing hydrogen nuclei together under pressures and temperatures so extreme that they merge, becoming something new, releasing energy not from the rearrangement of electrons, but from the rearrangement of the nuclei themselves. Nuclear fusion. The difference between a fire and a nuclear reaction is the difference between rearranging electrons and rearranging atomic nuclei. One happens at the outer edges of atoms. The other happens at their very core. The sun does not burn. It fuses. There's no oxygen involved, no combustion, no flame in any chemical sense. The light that reaches your window in the morning, the warmth that moves across a floor, none of it came from fire. It came from something older than fire, something that fire can only gesture toward. And yet we look at the sun and we think of flame, because flame is the closest thing we have ever held in our hands that resembles it. A small, brief, terrestrial echo of a process happening 93 million miles away. There are other ways that matter produces light without fire. Chemiluminescence, the production of light through a chemical reaction that generates almost no heat. You may have held it in your hands as a child, a thin plastic tube, bent until something inside it cracked, and then a soft glow, green or orange or blue, lasting through the night. A glow stick works because two chemicals, kept separate by a thin barrier, mix when the barrier breaks. Their reaction releases energy, and that energy emerges not as heat, but almost entirely as light. Cool light. light without burning. It is, in its way, the opposite of fire. Fire produces far more heat than light. Chemiluminescence produces far more light than heat. The same basic principle, a chemical reaction releasing energy, arriving at a completely different result. Fire is, among other things, inefficient. A well-designed wood stove, one with controlled airflow, insulated walls, a carefully managed burn, can convert more than 80% of the wood's stored energy into usable warmth. That is a remarkable achievement of engineering, the result of centuries of refinement. But an open fire, a campfire in a clearing, built the way fires have been built for 1,000,000 years, converts only about 10 to 15% of the wood's energy into warmth that reaches the people sitting around it. The rest rises. Hot gases climbing into the dark, light scattering outward in every direction, energy returning to the sky that the tree once borrowed from the sun, over years of slow growth, now given back in minutes. There is something almost generous about that. A fire does not hoard its energy. It releases almost everything it has, most of it upward, into the night. The people sitting around it receive only a small portion, and yet that small portion has been enough for 1,000,000 years. It has been enough. Fire shaped not only how humans ate and moved and thought, it shaped how they sensed the world. The ability to detect smoke at very low concentrations, just a few parts per million in the air, is almost certainly an evolved trait, something the human sensory system developed over hundreds of thousands of years of living with fire and of needing to know, before anything else, when fire was near. Smoke means something is burning. Something burning might be warmth and safety, or it might be danger approaching faster than you can see. The nose learned to decide. And this is not only true of humans. The smell of smoke triggers alertness in many mammals. Deer and elk have been observed moving away from smoke long before any fire becomes visible to them. Long before the sound of burning reaches them, the scent alone is enough. A signal carried on the air that something in the landscape has changed. There is a whole quiet language that fire speaks through smell. Some plants participate in it. When fire damages a plant, scorching its leaves, burning through its outer layers, the plant releases volatile chemical compounds into the air around it. These compounds drift to neighboring plants, and those plants, receiving the signal, begin to increase their own chemical defenses, thickening their tissues, producing compounds that make them harder to burn, harder to eat. A forest, in the presence of fire, begins to communicate. Not in any way that resembles thought, but in the slow, chemical way that living systems have always exchanged information through molecules drifting on the air, through responses that take minutes or hours rather than seconds. Fire enters the forest, and the forest responds, not just by burning, but by preparing, by passing something like a warning from one rooted being to the next. And the animals move, and the smoke rises. And somewhere, far above the canopy, the particles from that fire will drift for days or weeks, crossing distances that would have been unimaginable to the people who first learned to keep a flame alive through the night. All of this, the drifting gases over a marsh, the light of a glow stick fading toward morning, the warmth that reaches you from a fire, and the far greater warmth that rises away from it. The deer already moving through the trees before the smoke is thick enough to see, all of it is part of the same ancient process. Matter releasing energy. Energy moving through the world, finding its way, eventually, back to the dark. That smell after a fire moves through a pine forest. It is not simply the smell of burning. It is something older and more layered than that. The resins inside pine wood, compounds called terpenes, are released as the wood heats and breaks apart. They drift outward into the cooler air, and what reaches you is something between medicine and memory, sharp and clean and faintly sweet. Smoke from burning wood is not a simple thing. It is a mixture of hundreds of distinct chemical compounds, gases and fine particles, and volatile molecules that have been transformed by heat into something entirely new. Some of those compounds are antimicrobial. They inhibit the growth of bacteria. They slow the processes of decay. And somewhere, very early in human history, someone noticed this. Not in any deliberate, scientific way, but in the way that knowledge accumulates slowly through observation and repetition, and the quiet passing of understanding from one generation to the next. Meat hung near a fire lasted longer. Fish dried in smoke, kept through seasons when fresh food was scarce. The controlled use of smoke to preserve food predates writing by a very long time. It may be one of the oldest technologies we have, a way of borrowing fire's chemistry to hold back the inevitable. Smoke was, in this sense, a kind of gift that kept giving long after the flames had died, and fire gave other gifts as well. At least 30,000 years ago, and perhaps longer, someone took a piece of charred wood from a fire and drew with it. Charcoal, which is wood burned slowly in low oxygen until almost nothing remains but carbon, makes a mark that is precise and dark and surprisingly durable. It does not fade the way plant pigments do. It does not wash away easily. It holds its shape against stone. The oldest known art made with charcoal reaches back into a time so distant that the people who made it were anatomically identical to us, but lived in a world we would barely recognize. They moved through landscapes shaped by ice and fire and the slow migrations of animals. And in the evenings, by firelight, they made images. The cave at Lascaux, in what is now southern France, holds paintings that are roughly 17,000 years old. The animals there, horses, aurochs, deer, were painted using pigments ground from minerals and mixed with animal fat. The artists who made them worked by firelight, small lamps burning fat, casting a warm and unsteady glow across the curved stone walls. In that flickering light, the painted animals may have seemed to move, the shadows shifting as the flames shifted, the horses appearing to run as the light danced across them. Fire was not just the tool that made the art possible. It was part of the experience of the art itself, the medium through which it was seen. Fire was, as far as we can tell, the first artificial light source that humans used for creative and symbolic purposes. Before fire, after sunset, there was only darkness, the stars, on clear nights, the moon, when it was present. But nothing that could be carried, nothing that could be directed, nothing that could illuminate a wall deep inside a cave. Fire changed that. And for most of human existence, for hundreds of thousands of years, it remained the only thing that changed it. Every evening, for generation after generation, the light available to human beings after the sun went down was the light of fire. Warm, orange, flickering, low. It was the light by which people ate and talked and told stories and eventually closed their eyes. It was the last thing seen before sleep, night after night, across an almost incomprehensible span of time. The transition away from that to gas lamps and then to electric light happened within the last 150 years or so. In the full context of human history, that is almost nothing. A single breath at the end of a very long story. And the body has not entirely caught up. The circadian rhythm, the internal clock that governs when we feel alert and when we feel sleepy, evolved under conditions that no longer exist for most people. It evolved in a world where evenings were lit by fire, where the light after sunset was warm and dim and rich in the red and orange wavelengths that fire naturally produces. Blue light, the kind emitted by screens and by most modern electric lighting, suppresses the production of melatonin, the hormone that signals to the body that night has arrived. Firelight contains very little blue light. It is, in this sense, almost the opposite of a screen. It dims and warms as the evening deepens, rather than maintaining a steady, stimulating brightness. Sitting by a fire in the evening, it turns out, may be more compatible with the body's natural preparation for sleep than almost any other form of modern lighting. Not because fire is magical, but because the body learned, over an enormous stretch of time, to read firelight as a signal, a cue that the day was ending, that it was safe to let the muscles soften and the thoughts slow and the eyes grow heavy. The warmth, the flicker, the soft, irregular crackling of wood releasing its last energy into the air. These are not just pleasant sensations. They may be among the oldest signals the human nervous system knows, older than language, older than agriculture, older than any of the structures we have built around ourselves. The body recognizes them at a level that does not require thought. And so, lying here now, in the quiet, there is something in the stillness that is not so different from that. The day has given what it had to give. The light has faded. The body is warm. The mind is beginning, slowly, to release its hold on the details of the waking world. Fire is, in the end, a process of transformation, matter releasing the energy it once borrowed from the sun, returning it quietly to the dark. And you are part of that same ancient rhythm, breathing slowly now, letting the warmth settle, letting the thoughts drift like smoke into the still air above you. There is nothing left to tend tonight. The fire has done its work, and the dark is soft, and you can rest. The dark is soft, and somewhere in that softness, something continues. Not a fire now, not a flame you can see or touch, but the same quiet process, still unfolding. Matter releasing what it once held, energy returning to the world in the only way it knows how. Transformation. That is what fire has always been. Not a thing, but a becoming. A moment when something that was solid and still decides, in the presence of heat and air, to let go. And it has been letting go for a very long time. The oldest traces of fire in the rock record appear roughly 420 million years ago, long before there were hands to tend it or eyes to watch it. When the first land plants grew tall enough and dense enough to fill the air with oxygen, lightning found them, and the world burned for the first time. Charcoal, pressed into ancient stone, is still there, a record written in carbon, patient and permanent, of fires that no living thing remembers. Fire was here before us. And then, slowly, we arrived. Somewhere around 1 million years ago, perhaps longer, the evidence is still being weighed. A hominin crouched near a source of heat and did not run from it. In a cave in what is now South Africa, burned bone and plant ash settled into the earth and waited nearly 1 million years to be found, to tell us something about who we were becoming. Homo erectus, a creature not quite us, but not entirely unlike us either, standing at the edge of something new. The fire did not just warm them, it changed them. Cooked food releases more energy than raw food. The same roots, the same flesh, the same seeds, transformed by heat into something the body could absorb more completely. Calories that had been locked away became available, and the body, given more energy than it had ever reliably had before, began to spend it. On the brain. The human brain is an extraordinary expense. It consumes roughly 1/5 of everything the body takes in. In the animal world, that is an almost reckless investment. But fire made it possible, unlocking energy that paid, over hundreds of thousands of years, for the slow expansion of something that could think and remember, and eventually sit by a fire and wonder about it. There is something quietly circular in that. The jaw grew smaller as food grew softer. The skull, no longer constrained by the architecture of heavy chewing muscles, had room to change shape. The face flattened. The forehead rose. The creature that emerged, over vast stretches of time, was one that could look into a flame and ask what it was. And fire gave them the night. Before fire, darkness was a boundary. After fire, it became a gathering place. People sat together in the hours after sunset, and something shifted in what they said to each other. The practical talk of the day, where to find food, how to move, what to avoid, gave way to something else. Stories. The names of people who were no longer there. the shape of things that had not yet happened. Firelight may have been the first stage on which the human imagination performed, and the body learned, over all those long evenings, to associate the warmth and the flicker and the low, irregular sound of burning wood with something safe, something that meant the day is done, the cold is held back, you are not alone, you can rest. That learning did not disappear. It is still here. Studies have found that watching a fire lowers blood pressure, not a little, but measurably and in proportion to how long you watch. The longer the fire, the quieter the body becomes. Researchers have suggested this is not coincidence, that the human nervous system carries, somewhere in its oldest architecture, a response to firelight that was shaped across millions of years of evenings just like this one. The flicker falls within frequencies that overlap with the brain's own rhythms of relaxed wakefulness. The warmth arrives as infrared radiation, pressing gently through the skin. The sound, those soft, irregular pops of water vapor escaping from wood, lands on the ear in a pattern that does not demand attention, only receives it. And firelight itself is gentle on the body's clock. Rich in red and amber, low in the blue wavelengths that tell the brain it is still midday. Sitting by a fire in the evening, the body is not confused. It knows, in some wordless way, that the light is changing, that the world is winding down, that sleep is near. For most of human existence, this was simply the evening. The fire burned lower, the voices grew quieter, the eyes grew heavy. And then the fire would go out, and the dark would come, and the body would rest until the light returned. That rhythm is very old, older than any word for it. The word fire itself reaches back to the earliest recoverable layer of human language, Proto-Indo-European, a sound something like pyrar, spoken by people who had never heard of electricity, or glass, or the idea that one day their distant descendants would lie in warm rooms and listen to someone describe the history of the flame. They knew fire the way you know breathing, as something simply present, something the world required. And in a sense, it still does. Fire moves carbon through the world, releases what trees have spent years gathering from the air, returns it to the cycle that will, in time, become new growth, new wood, new fuel for fires not yet imagined. It is one of the mechanisms by which the living world breathes in and out across geological time. Even the sun, which is not fire in any chemical sense, which fuses hydrogen into helium in a process entirely unlike combustion, even the sun is, in its way, a transformation. Energy that has traveled 8 minutes across empty space to fall on leaves, to be stored in wood, to be released one evening in a small flame that warmed a face that looked up and wondered. All of it connected. All of it, the same energy, moving through different forms, across different scales of time. 100 million years of sunlight, resting in a piece of wood, released in an evening, returned to the dark. There is nothing urgent in that. Nothing that requires anything of you now. The transformation is already complete. The energy has moved on. And what remains is stillness. The breath slowing. The body settling into the surface beneath it. The thoughts growing, less distinct, less insistent, drifting the way smoke drifts when there is no wind to direct it, rising gently, dispersing, becoming part of the air. Somewhere, a fire is burning, low and quiet, tended by no one, needing nothing, just the slow release of what was held, and the dark receiving it, softly, without hurry, the way the dark always has.